Hey guys, today I'm going to teach you how to graph a system of inequalities. By the end of this lesson, you'll be able to identify the solution set for a system of inequalities. So go ahead and get out your binder, turn to the math section, and let's go ahead and take some notes. The first thing I want to do is graph two separate linear inequalities. I'll go ahead and do them now, but if you want to, you can pause and try it by yourself first. I know the first one has a y-intercept at 6 and a slope of -1, so I'm going to keep putting my points down 1 and over 1. I can also go up 1 over 1. The line should be solid because there's an equal to sign in the inequality symbol, and then I need to shade below the line because it says y is less than. Deal for the other one, the y-intercept is at -6, the slope is 1. And go up 1 over 1 or down 1 and to the left 1. I'm going to leave it dotted or dashed because there's no equal to sign in the inequality symbol, it's just a greater than sign. I also need to make sure I shade above the line on this one because it says y is greater than. Now that we have the graphs of the two separate linear inequalities, let's take a second and answer these three questions. Okay, so for A, you could have listed any ordered pairs that represent solutions that are in the shaded region for both of these graphs. So 6, 0 is only a solution to the first one because it's on the boundary line and it's included because there's an equal sign. On the second graph, the boundary line is dashed. So when we hit that point, it's not actually included in the solution set. If you plugged 6, 0 into this inequality, you would get 0 is greater than 0, and that is a false statement. So that's how you know it's not going to be included in the solution set. Then finally, if they were graphed on the same coordinate plane, you could identify the solution set to both inequalities as the places where they overlap. So that is what we're going to get into today. A system of inequalities is a set of two or more inequalities with the same variables. The solution set to a system of inequalities makes those ordered pairs true for all the inequalities in the system. And then this is the important part. On a graph, it's going to be the overlap of the shaded areas, and that's where we're looking at the actual solution set for both inequalities. Basically, you're graphing two inequalities on one coordinate plane. Take a second and see if you can graph the red inequality here first, and then press play when you're ready to check. All right, so this is the inequality that is listed first. I did it in red. It should be shaded below the line because it says less than. Then we look at the blue one, and we're going to do this one on the same coordinate plane. So start at -3, then your slope is down 1 over 1, and keep on plotting those points. You can also go up 1 and to the left 1. When you have your points plotted, go ahead and connect them because this is a solid line because it has the equal to sign, and then shade above the line because it's a greater than sign. Now, normally when we solve systems, we're looking for the one point where they intersect. But because this is a system of inequalities, we're actually going to look for the shaded regions that are overlapping. If you have highlighters, this might be cleaner. And just for the sake of this, I'm going to erase the part that's not overlapping for both these graphs. What you should realize is that the part that's overlapping is the red and the blue region. So this area is the solution set for this system of inequalities. So the point 0, 0 is in the overlapping shaded region. That is a solution for both inequalities. That's why it's a solution to the system of inequalities. Is 4, -3? Yeah, 4, -3 is in the overlapping shaded region. But when you look at the point -2, 3, you can see that point is only going to be covered by the blue. If it's not covered by both, that means that this point is not a solution to the system of inequalities. We can see that that point's not in the overlapping shaded region visually, but we can also test it algebraically. If we plug that point into the inequality, like for example the red one that we did first for the y and the x, and we solve it, you would end up with the statement 3 is less than -2, and that's false. That's not a true statement. If you plug that into the blue inequality, it would work, but it has to work for both of them. That's the key difference when you're looking at solving a system of linear inequalities versus just one linear inequality. The solutions have to work for both inequalities, so it would be in the overlapping shaded region. Keeping that in mind, go ahead and try number 2 as much as you can by yourself and press play when you're ready to check. All right, I'm going to graph this system with yellow and green. If you can't see the y-intercept, it means it starts at 0. So I start at 0, and then I go up 1 over 2, and I continue that pattern of plotting points until I have enough to connect them. It's a solid line. There's an equal to sign. Then we shade below the line because it says y is less than. Before graphing the next inequality, I want to put it in slope-intercept form. So I want to get rid of the x, so I subtract it from both sides. Y is less than -4 minus x is the same inequality, but now it's in slope-intercept form. So I can start at -4, and then my slope is -1. I'm plotting points down 1 over 1, down 1 over 1. I can also go up 1 and to the left 1. I'm going to leave them unconnected and dashed or dotted because it doesn't have the equal to sign here, but I am going to shade below the line because it says y is less than. The solution set for this system of linear inequalities is where they overlap. So if you had highlighters, it's where the colors are on top of each other. If you're looking at a digital software, sometimes it's darker in that region. I don't have that, so I just erased the solutions that are only going to be true for one of the inequalities, and I kept the overlap where it's true for both. So this area is the solution to the system of linear inequalities here. You need to determine if these three are solutions to the system. -3, -6 is in the overlapping shaded region. All of the points in that overlapping shaded region are solutions to the system. -5, 0 only works for the green inequality. It would only be in the green region, not the green and the yellow. And then 0, -4 is on the dashed line, so it does not count as a solution for both inequalities. Now you should try both number 3 and number 4 by yourself and press play when you're ready to check. This is how you graph y is greater than or equal to -6. Before you graph the next line, you'd want it in slope-intercept form. You should have y is less than 2 minus 1/2 x. Put that line at 2 and then go down 1 over 2 or up 1 to the left 2. Keep it dotted or dashed because there's no equal to sign. And then we want to shade below the line. But the only solutions is where there's orange and purple, where both are intersecting. So the solution set is in this overlapping shaded region. For number 4, the first one, you start at 5 on the y-intercept, and then you would go up 2 over 1 from each point. You could also go down 2 and to the left 1. Keep the line dashed because there's no equal to sign, and shade above the line because it says y is greater than. Before you graph the next line, you would want it in slope-intercept form, so you should have y is less than or equal to -4 plus 2x. These two lines have the same slope, so you should do the same thing, up 2 over 1 or down 2 to the left 1, same thing. This one is a solid line because it has that equal to sign. We shade below the line because it says y is less than. This is the correct graph for this system of inequalities. What do you think it means about the solution set for this system? In this particular instance, there's no overlapping shaded region. So for number 4, we could say that there's no solution to this system of inequalities. Brings me to number 5. Toby believes that if the lines in a system of linear inequalities are parallel, there will always be no solution to the system. What do you think? Do you agree or disagree? Explain. I disagree with Toby. It depends on the inequality symbols for these. For example, in this one, if we had this reverse, we would be shading above the line, and then this area would be the overlapping shaded region. So it really depends on the inequality symbol. I know we think whenever we're looking at systems of equations that are parallel, there's no solution, but because the inequalities represent the shaded areas, it just depends on which way that they're facing to create that solution set. For a problem like number 6, the graph is already shown to us. We just have to write the system of inequalities represented based on that. So I'm going to start with the blue line. If it was an equation, it would be the graph of y equals 6, but it's not. It's an inequality because they're shading. And if I look at the line, I can see that on the blue area all the way down below is where it's shaded. Because it's solid, it has to have that equal to sign. So I put y is less than or equal to 6 for the blue line. See if you can write an inequality statement for the red line and then press play and ready to check. The y-intercept is at 0, so I can put plus 0 at the end, but I don't have to. It looks like it's going up 3 over 2. If you look at the scale on the graph, it's actually up to 6 over 4. 6 over 4 is the same thing as 3 over 2. If it was just the graph of this line, it would be y equals 3 over 2x, but it's not. It's got a dashed line, so I know it's going to be an inequality symbol. I also see shading, and since we're shading above the line, we're going to use a greater than sign. Here's 3 ordered pairs that are solutions to this system. You can pick any points that are in the shaded region that's overlapping. So on this graph, it's the darker shaded region. See if you can pick 3 more ordered pairs that are solutions to the system. And then finally, just so you have some non-examples, here are 3 ordered pairs that are not solutions to the system. They're either only going to work for one or they're not going to work for either. Those are where we're looking at where they're not in the shaded overlapping region. All right, number 7 is our last one, and it's a word problem. It says Jessica bought hot dog buns and hamburger buns. That's our X and Y. And the total number of hot dog and hamburger buns was less than 50. So there's our first inequality. It says Jessica bought more hot dog than hamburger. So we can use this system of inequalities to represent the situation. First thing we're going to do is graph it. So take a minute and graph the system. This should be your first inequality. This should be your second inequality in red. Your solution set is the overlapping shaded region. To answer the next question, look in the overlapping shaded region and list a possible combination of hamburger and hot dog buns that Jessica could have purchased. I said 10 hamburger buns and 25 hot dog buns. You can see it's in the overlapping shaded region for both. You could have said a few different answers for that one. So then the last question is, are there any ordered pairs in the solution set that do not make sense with this problem? Yeah, so since this is a real-life example, even though the negative values are part of the solution set for this inequality, it doesn't make sense for them to be considered for this real-life system. Only these numbers make sense with this system. It also doesn't make sense to have any decimal or fraction values since we're talking about the number of hamburger buns and hot dog buns. All right, that's it. Thank you for watching. If you have any questions, please let me know. Bye!